Dear students, in this video we will learn error detection and correction techniques. This is one of the main activity performed in the data link layer. If the frame is corrupted between two nodes, it needs to be corrected before it continues its journey to other nodes. And to some extent we are aware of the error detection and correction techniques, but still we need to study it in detail. There are mainly three different techniques for error detection and correction. One is parity, next is checksum, and another is CRC or cyclic redundancy check. Then let us think about error correction techniques. Here we can see two different terminologies. One is error detection and another is correction. How to detect error and how to correct error. Detection is possible and it is what the technology used. Error correction techniques. What is error correction is when the receiver detects some errors in the data received, it executes error correcting code or some algorithm to perform error correction, and it executes error correcting code which helps to auto recover and correct some kinds of errors. So some kinds of errors can be corrected, but not all errors can be corrected. So to correct the error in the data frame, the receiver must know exactly which bit in the frame is corrupted. To locate the bit in the error, the redundant bits are used as parity bits for error detection. Redundant bits means extra bits are added, and the parity bits are used for finding the position of the error bit. And very small amount of error correction is possible, and most of the techniques are following error detection and the retransmission technique. If once the error is detected, it will be reported to the center and retransmit the error packets again or error frames again. That is what the technology used. So error detection is the one which is actually performed in practical scenarios. And we need to study in detail about the error detection. Then let us think about error detection in detail. Error detection and correction bits are known as redundant bits or redundancy. And we use EDC in this figure, and which represents the error detection and correction code or extra bits added to the actual data, and D means it is the actual data, the data protected by the error checking, and may include header fields. In some cases, header fields are also added as a part of the data. Not in some cases, in all cases, the headers will also act as a data. That is, headers contributed from the upper layer to the lower layers, and these headers will be the part of the data or encapsulates the headers as a part of the data by upper layer to each lower layer. Then error detection is not 100% reliable, and the protocol may miss some errors, but it is happening very rarely. Then larger error detection and correction codes or larger extra bits yields better detection and correction. So actually what is happening in error detection is actual datagram is there and its length is D bits. Capital D represents the data and capital EDC represents the error detection and correction bits. And it is moving through the error prone channel or link, and at the receiving side D is represented as D dash. D dash means Actually, D and D dash must be same. Otherwise, we can think that there some error is occurred. EDC is represented as EDC dash. Then all the bits in D dash are okay. Means it will be detected based on the computation of EDC at the destination side. EDC dash at the destination is the computed value. The computed value of the error detection. So EDC dash represents the computed value at the receiving side. From the D dash, it will compute EDC dash. And if this EDC dash and the received EDC are same, then we can assume that the data is okay. Otherwise, it will detect some errors. This is a concept which we studied in the previous module. In parity, there are two different types of parity. One is single bit parity, another is two-dimensional bit parity. For case of single parity, there can be even parity and odd parity. Odd parity means total number of ones in the data must be odd, including the parity bit. And in case of even parity, total number of ones in the data, including the parity, must be even. And this is the simplest form of error detection and correction. Actually, for error correction, in order to identify the position of the error, we can use parity. Actually, parity itself is not correcting the data. So, here we can see that data and the parity is computed as 0. Let us count the total number of ones in the data. 3 plus 2, 5, 6, 7, 8, 9. So, it is odd number of ones. So, here it is using odd parity. At the receiving side, the receiver also performs the same calculation and find the parity bit. If the parity at the sender side as well as the computed parity at the receiving side are same, then the data is received without any error. This parity calculation is already you might have studied in the UG classes. And the two-dimensional parity means the data is divided as rows and columns. So the entire data is represented as the bits of D11 up to D1J. 1 stands for the row 1. And for the second row 21, 22, etc. 2J. And the ith row and the last bit will be ith row, jth column. So there are a row as well as column. Column is the index represented at the right side and the row is index represented at the left side. Ij means ith row, jth column. So for every row, it is computing the row parity as well as for every column, it is computing the column parity. Then this entire row parity plus column parity plus data is moving to the destination. And the same computation is performed at the receiving side. What is the benefit of two-dimensional parity over single bit parity is, here we can identify the position of the error bit, by finding a mismatch at a particular row column intersection point. In case of single parity bit, multi-bit errors, or even for case of even parity, even bit errors cannot be identified, and for odd parity, odd number of bit errors cannot be identified. Next is checksum. Checksum is also we studied in the third module as a part of the transport layer. The concept is same, the computation and everything is same. Just review of the same thing is here explained. The goal is to detect errors or finding the flipped bits. And at the sending side, it computes a 16-bit ones complement addition. And this is add at the end of the data. It is attached to the end of the data as checksum field. At the receiving side, same calculation is performed. And if the computed checksum and the received checksum are equal, then no errors, otherwise error is detected. So you need to reproduce all the calculation and all other things here again if the same question is asked for the 6 marks part. The next error detection technique is CRC, cyclic redundancy check. This is the most powerful error detection technique and it is also known as polynomial codes. This is an important part and you must know how to compute the CRC for a given data and that is as in the previous question papers also. Here capital D represents the bits of data in binary. Then the sender and the receiver must first agree upon a generator polynomial G, that is on a common agreement between the sender and the receiver. And the number of bits for G is R plus 1, where R is the extra bits added to the data. Extra bits or redundant bits. In case of parity, we add parity bit as a redundant data. In checksum, the computed checksum is the redundant data. Here, the computed CRC bit is the redundant data. Redundant data means data plus the calculated value for the data. The purpose is to detect the error. And the number of bits for G is R plus 1, where R is the redundant bits. Then choose R CRC bits, R number of bits, such that D plus R bit pattern is exactly divisible by G. D together with R is exactly divisible by the generator polynomial. And the computation is explained in the next slide in detail. The receiver and sender is on an agreement for the selection of G. And the DR group, this is what the data sent by the sender. And at the receiving side, the same computation, modulo 2 division is performed. And if the remainder is 0 at the receiving side, then the data is having no error. Otherwise, the data is having some error. This is what the technique used in CRC. So, with the help of CRC, what is the advantage is we can detect all burst errors less than R plus 1 bits. Now let us do a CRC computation for the given data. The data D is given 101110. This much is the data part, and the generator polynomial G is equal to 1001. That is also given, and we are adding 3 extra bits because the number of bits in the generator polynomial is given, that is 4. So R plus 1 is the number of redundant bits plus 1 is equal to the number of bits in the generator polynomial. So here we are adding 3 zeros at the end of the data. Then just like the normal division, consider the left 4 bits here up to here. Then the data is having 1 at the leftmost bit, and generator polynomial is also having 1. That time we put 1 here, then 1 time 1001 is this data. Then do instead of normal subtraction, do the XOR operation. If the two data are same, the XOR will result to 0, and if the data are different, XOR will be 1. So here it will be 0, and here also it will be 0. Then ignore the leftmost 0. Now we have 0 1 0 1 is the data. 0101 is the data, because this one is taking this one to this position. Okay, for the next iteration we are considering one more bit from the data, just like the normal division. That's why the one comes here. So 101 is the data here. Here also 10. Since this is 0 and this is 1, we put 0 here. So 0 times 1001 is 0. So actually here it is 0 0 0, because it is 0. Then here it is subtracting. Instead of that, we are doing the XOR operation. Here it is 1, here it is 0, here it is 0, and this 0 is ignored. Always we ignore one leftmost 0. Then the next bit position onwards we will consider. Here this is a bit. So this bit as well as the first bit of this generator polynomial, these two are 1. So you have to put 1 here. Then 1 time 1001 is this one here. So do the XOR operation. Here it is 1, here it is 1, and these two are 0. Ignore the 0. Then take one more 0 from the top to downward. Then this is what the data. Since here it is 0 and the data is 1, so we are taking 0 here, and 0 times 1001 is again 0 here. So do the XOR operation. 0 here, 1 here, 1 here. Then take next bit from here to this position. Then here there were only 1 0, so we are not considering this 0 and taking this 1, and this is 1, so take 1 here, and 1 time 1001 is 1001 here. Then do the XOR operation. 1 0 is 1 here, 0 here, 1 here. Then the next bit position is taken to here, and the leftmost bit is 1 here, 1 here, and this is also 1 here. So 1 time 1001 is again 1001. Then compute this thing. So XOR is 1 here, 1 here, 0 here, and 0 here. Take the number of bits same as that of the R. Actually here we are added 3 bits, so consider the rightmost 3 bits from the remainder part. Okay, so now the after division, after modulo 2 division, we got the remainder as 0 1 1. That 0 1 1 is added to here. Actually 1 0 1 1 1 0 is the data. Again we added 3 bits plus 0 1 1, the remainder. So 0 1 1, and the same data is replicated here. So this is what the actual data D comma R. This will be sent to the sender side, and the same calculation is performed at the receiving side. So since we are added the remainder to this part, after the division, the same division, after dividing with G, generator polynomial 1001, we get the remainder 0. If the remainder is 0, means there is no error. If the remainder is 0, there is no error. Otherwise, we can say that it is error. Okay. What will do if the error is happened? Then the request will be generated for retransmission. This is how the CRC is calculated. This is a part extracted from your previous question paper for the computation of CRC, and you must compute the CRC with the generated polynomial is here given it as 10101. This is what the generator polynomial, and this is what the data. Along with the data, you must add 3 zeros and do the computation and find the remainder. Then the receiving side also do the same calculation and show that the remainder is 0.